Hello everyone, welcome back to my channel. In the last video, we discussed that what happens when the alternating voltage is applied across individual inductor and capacitor by J operator method. So, we are going to learn what happens if an alternating voltage is applied to the combination of LC circuit, in the sense inductor and capacitor circuit. So, which combination we are studying here? That is a parallel combination of LC circuit. So, let us consider an inductor of an inductance that can be represented by L, which is connected to a capacitor of a capacitance that can be represented by C. So, which are connected across an AC source that can be represented by V is equal to V naught e raised to j omega t, because here we are discussing the concept that is a parallel combination of inductor and capacitor circuit by using a J operator method. Here we know that the alternating voltage across AC source, and this one is an AC source we use, that can be represented by V is equal to V naught e raised to j omega t. Let us consider this one as an equation number 1. Here V represents the instantaneous voltage, V naught represents the peak value of voltage, and e raised to j omega t we are representing instead of a sign of omega t. So, we are consider e raised to j omega t in J operator method. Now, the current flows through the circuit, and here the current divides because we are connected LC in parallel. Therefore, the current divides, the current flows through that inductor that can be represented by IL, the current flows through that capacitor that can be represented by IC. Now, the current flows through that inductor, the current flows through the inductor that can be represented by IL, which is equal to your V naught divided by omega L e raised to j of omega t minus of pi by 2. So, we know that by using a phasor diagram, if we consider an inductor, the current always lags behind the voltage by pi by 2. If we consider the capacitor, the current leads the voltage by pi by 2. Here we are consider an inductor, therefore, the current is always lags behind the voltage by pi by 2. Current lags the voltage by pi by 2. Therefore, we are getting this expression. Let us consider this one in equation number 2. Now, the current flows through that, capacitor, through that capacitor. So, that can be represented by IC. Therefore, IC which is equal to V naught divided by 1 over omega c e raised to j omega t plus of pi by 2. So, here we took a minus pi by 2 and here we took a plus pi by 2, because in case of an inductor, current always lags behind the voltage by pi by 2, but in case of a capacitor, current leads the voltage by pi by 2. Therefore, we are using a positive sign here. Let us consider, and this can also written as IC, which is equal to V naught omega c e raised to j omega t plus of pi by 2. Equation number, that is 3. Now, the total current flows through that circuit that can be represented by the total current through the circuit, So, that can be written as I is equal to IL plus of IC. We know that IL that can be written as V naught divided by omega L e raised to j omega t minus of pi by 2 plus of, so IC that can be written as V naught omega c e raised to j omega t plus of pi by 2. Therefore, I can be written as, so here we are considering a V naught as a common term in the both cases, and the e raised to j omega t, e raised to j omega t is a common term. Therefore, V naught e raised to j omega t into 1 over omega L into remaining part is e raised to minus of j pi by 2 plus omega c e raised to plus j into pi by 2 we are going to get. Let us consider this one as an equation number 4. We know e raised to j pi by 2, this can be written as cos of pi by 2 plus j into sin of pi by 2. Similarly, e raised to minus of j pi by 2, that can be written as cos of pi by 2 minus of j into sin of pi by 2. Here e raised to j pi by 2, its value becomes a j in j operator method, and e raised to minus of j pi by 2, this can be written as minus of j. Now, equation 4 can be written as I is equal to V naught e raised to j omega t into, so 1 divided by omega L, 1 by omega L, instead of e raised to j minus of j pi by 2, in the sense we have to consider the minus of j plus omega c e raised to plus j pi by 2, that can be considered as a plus j. Therefore, I is equal to V naught into j e raised to j omega t, and here omega c minus of 1 divided by omega L we are going to get, because minus sign is there, therefore we wrote after omega c. So, let us consider this one as an equation number 5. We know the total impedance in the circuit, So, we are connected inductor and capacitor, they are in parallel. Therefore, the impedance that can be represented by 1 over Z is equal to 1 divided by ZL. So, impedance across inductor plus of 1 divided by ZC, impedance across a capacitor. But here we have to know that Z of L, which is equal to j omega L, and ZC, which is equal to 1 over j omega C. Now, this can also written as Z is equal to ZL into ZC divided by ZL plus of ZC. Now, substitute the value of ZL and ZC here. Z is equal to ZL, that can be written as j omega L, ZC, that can be written as 1 over j omega C. So, divided by j ZL, that can be written as j omega L plus of 1 over j omega C. So, this can also written as Z is equal to j omega L, and here denominator j omega C we are going to get. Therefore, if we simplify that one, L divided by C we are going to get, and in denominator, so j omega L plus 1 over j omega C is there, that can be written as j omega L. If j bring denominator to numerator, we are going to get minus of j divided by omega C. Therefore, Z is equal to L over C divided by j into omega L minus of 1 divided by omega C we are going to get. But in the case of in the equation number 5, here we are getting omega c minus of 1 divided by omega L. Therefore, by simplifying and this expression into j L over c, so this can be written as omega c minus of 1 divided by omega L. So, take a common L by c and we are going to get omega c minus of 1 divided by omega L. Let us consider this one as an equation number 6. Now, we know that the current equation I is equal to V naught j e raised to j omega t into omega c minus of 1 divided by omega L. Now, by comparing these two equations, let us consider equation number 7, comparing these two equations. Therefore, the current equation that can be written as V naught e raised to j omega t. So, here 1 over omega c minus of omega L in the sense z, therefore, we are considering z here. So, let us consider this one as equation number 8. Here the j in numerator and j in denominator, they get cancel each other, therefore, remaining term is I is equal to V naught e raised to j omega t 1 divided by z. Now, this z can be written as V naught e raised to j omega t divided by I, we can represent impedance value in the sense z is equal to V naught e raised to j omega t divided by I. This represents the total impedance in that parallel combination of L and C circuit. So, at a resonance circuit, the current flows through that both the branches, in the sense we are going to observe the inductor and capacitor. The current flows through that inductor and capacitors are equal. Therefore, when the current is equal, the net current flows through that circuit which is equal to 0. Therefore, this equation 7 that becomes 0 is equal to the net current which is equal to 0. Therefore, I is equal to 0. 0 is equal to V naught j e raised to j omega t omega c minus of 1 divided by omega L we are going to get. Therefore, this can be written as omega c minus of 1 divided by omega L which is equal to 0. So, at a resonant circuit, we can represent omega as an omega r, because resonant circuit omega RC which is equal to 1 divided by omega r into L. Therefore, cross multiply this, omega r square is equal to 1 divided by LC. Omega r which is equal to 1 divided by square root of LC. Here omega r that can be represented by 2 pi f r which is equal to 1 divided by square root of LC. Therefore, f r which is equal to 1 divided by 2 pi square root of LC. So, this expression that represents the resonant, the frequency. At the resonant frequency, we know that there is a maximum impedance takes place. If the maximum impedance takes place, the current flows through that circuit that becomes very less, and it also becomes equal to that 0. Therefore, the resonant frequency that can be represented by 1 over 2 pi square root of LC. At resonance frequency, the parallel LCR circuit offers infinite impedance. Therefore, the current flows through that the circuit is equal to 0. Therefore, the current will be is equal to 0. So, this explains about the parallel combination of L and C circuit. And the next concept is sharpness of a resonance. We know that in series LCR circuit, in series LCR circuit, the maximum current flows through that circuit and the minimum opposing force, in the sense resistance or impedance in the circuit. Therefore, if we observe the resonance curve along x axis and this one is y axis, let us consider the frequency along x axis and the current along y axis. As the frequency increases, the current also increases and it decreases. So, let us consider this is for R1. As the frequency increases, the current also increases and it decreases for if you further increase. Let us consider this one is R2 and this is for R3. And this represents a resonant frequency. Here it is the maximum value of a current that can be represented by I naught. In the sense, as the frequency increases, the current increases and it reaches a maximum peak value and after decreases. Here we took R1, R2, R3. Here R1 is greater than R2 is greater than R3. In the sense, as the value of resistance decreases, the current value increases. So, we are going to get the peak value of a current, that is I naught here. The resistance decreasing, R1 is greater than R2 greater than R3. Therefore, resistance value decreases, the current value increases. Therefore, we can call it as series LCR circuit is an acceptor circuit because it accepts or it allows the maximum current flows through that circuit. Therefore, in series LCR circuit it is also called as acceptor circuit. But in case of in parallel LCR circuit, in a parallel LCR circuit, if we observe the graph, so let us consider this one is an x axis and this represents a y axis. Along x axis we took a frequency along x axis and the current along y axis we do. So, here in case of a parallel LCR circuit, the current decreases and it reaches a minimum value and then again current increases. So, therefore, this value that represents the minimum value that we can call it as I minimum, the minimum value for the resonant frequency. So, here the resonant frequency in the sense the frequency at which the maximum current flows through that circuit. In series LCR, the frequency at which the minimum current flows through that circuit in parallel LCR circuit. Therefore, this parallel LCR circuit we can also call it as rejector circuit because the impedance is maximum, therefore, the current flows through that circuit is minimum. It does not allows the current flows through that circuit, therefore, we can also call it as rejector circuit. Based on this, they explain the quality factor. The quality factor that can be represented by Q. So, here the sharpness of a resonance curve which is determined by this quality factor, a sharpness of a resonance curve which is determined by a quality factor. Here the quality factor that can be defined as the ratio of either inductive reactance or capacitive reactance to that total resistance flows through that circuit, that we can call it as a quality factor. The quality factor that can be represented by Q, which is equal to ratio of inductive reactance to that total resistance flows through the circuit, that we can call it as a quality factor, or the ratio of capacitive reactance to that total resistance in the circuit, that we can call it as a quality factor. The ratio of inductive reactance to the total resistance flows through that resonant circuit, that we can call it as a quality factor. Here the ratio of capacitive reactance to the total resistance flows through that circuit, that we can call it as quality factor, that can be represented by Q. This can also written as Q is equal to J omega L divided by R, or here Q is equal to 1 divided by J omega C into R. So, and this is an expression for the quality factor. Here quality factor that can also defined on the basis of half power factor. So here we know that the current and the frequency, as the frequency increases, the current increases and it reaches a maximum value, and this we are considered I naught. For a particular frequency, that is a resonant frequency. Here half power frequency they mention, half power frequency. Half power frequency in the sense the frequency at which the power is half of that maximum power frequency, that we can call it as half power frequency. Half power frequency, let us consider a maximum power that can be represented by P max, and half power frequency that can be represented by P max divided by 2, that is equal to P. The half power frequency in the sense the frequency at which the power is half of that maximum power frequency, that we can call it as half power frequency. So here half power frequency, we know that an expression I naught divided by square root of 2. So this represents the value of half power frequency. Therefore if we cut it this curve, resonance curve, we are going to get two values, that is f1 and f2. So based on this, the quality factor that can also defined as the ratio of quality factor that can also defined as the ratio of a resonant frequency to that bandwidth. Here the bandwidth that can be represented by f2 minus of f1, the ratio of resonant frequency to that bandwidth at the resonance, that we can call it as. So quality factor based on half power frequency, quality factor that can be defined as the ratio of resonant frequency to that bandwidth of a resonance curve, that we can call it as a quality factor.